Bismillahir Rahmanir Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, dear students. As you know that in the last few lectures, we have talked about the sequence networks, and we have covered in the last two lectures the sequence networks of the Y-connected loads, transmission lines, and also in the last lecture, just the lecture before this one, I have also covered the rotating machine. So now in this lecture I will end this discussion on the sequence networks, where I will talk about the sequence networks of the transformers, and then with the knowledge that you have gained, we will also solve a particular example. So before starting the transformer, let me quickly revise the contents of the last lecture. So we discussed that the transmission lines offered the same impedance to the positive and negative sequence currents. So that's why the positive and negative sequence impedances are the same. So the geometry offers the same impedance. But in the case of the zero sequence network or zero sequence impedance, because that involve the current where it flows through the impedance to the ground. So x0, which is the zero sequence impedance, it is a sum of x1, which is inductive reactance representing positive sequence, plus 3xn, and we have already discussed this factor 3, and xn, which is the impedance to the ground, it is equal to 2 pi frequency 0.2 natural log of dn over d, where dn is a distance of the transmission line to the ground and d is the distance between the transmission lines. And then I also discussed that z0 is approximately taken as 3xn, where xn is the inductive reactance to the ground. So we discussed that z1 and z2, they are equal because the geometry represents present or offer the same impedance to the positive negative sequence currents. But in the case of the zero sequence current, where impedance to the ground is also involved, then it is approximately equal to 3xn, and with the help of this particular equation, the inductive reactance to the ground can be calculated. Afterwards, we took the case of the rotating machines, where we discuss about the the loaded synchronous generators, and we took this particular case where the neutral point was connected to the ground through impedance Zn, and then we determined the sequence networks, and also we found that the sequence impedance have a matrix which is a diagonal matrix, and the zero sequence impedance is equal to the Zg, which is the impedance associated with each phase, plus 3Zn. This term 3 again, or this factor 3 again, is appearing. So Z0, zero sequence impedance, is equal to Zg plus 3Zn, and the positive and negative sequence impedances were the same. However, in practice, this is not the case. Positive sequence impedance is not equal to the negative sequence impedance. Usually, the positive sequence impedance is taken either the steady state inductive reactance, transient inductive reactance, or the subtransient inductive reactance. And Z2, which is the negative sequence impedance, it is approximately taken as the subtransient inductive reactance. However, the leakage, or the zero sequence impedance, it is taken as the leakage reactance, which could be 0.1 to 0.7 times the inductive subtransient inductive reactance. So now we discuss, and even when I will solve a problem today, we will consider these situation where in practice the three are different. So I will solve a problem and then we will also consider these this fact. And we then found, or we derived the sequence networks of the synchronous generator, and we made some observations. We discussed that only in the positive sequence network we have voltage source. In the other two sequence networks, which is the zero and the positive and the negative sequence networks, there are no voltage sources. Also, we discussed that the positive and negative sequence currents, they do not flow through the impedance to the ground, which is ZL, and only the zero sequence current flow through the ZL. And we also discussed that if, let's say, the neutral point is not connected to the ground, then the zero sequence current will be zero. And some other observation that we made were that these three sequence networks, they are not coupled and one can solve them separately. So these were the observation that we made in the last lecture. Now we have covered these three parts, or we have talked about the sequence networks of the Y-connected loads, transmission lines and rotating machines. In particularly here we considered the synchronous machines. One can also talk about the synchronous motors and also the induction motors, but anyhow that you may learn sometimes later in some other courses. So I will restrict the discussion of the rotating machine only to the synchronous generator. So now let's talk about the transformers. So now we will talk about the sequence impedances of the transformers. So let's talk about the sequence impedances of the transformers and then solve a example to get a bit more clear understanding of the theoretical concepts. So now we will start the discussion with the sequence impedances of the transformers. So first of all, the important point is that transformers are modeled with series leakage impedance only. If you remember, we discussed that when we were discussing the per unit quantities, that transformers, the actual impedance of the transformer could be different on both sides, on the primary side as well as on the secondary side, because if you remember, we discussed about the the base impedance, and because base impedance is related with the square of the voltage, nominal voltage, divided by SB, and since transformer have at least two voltage levels, primary secondary side voltage levels, so that's why for the same power rating the base impedance could be different, and correspondingly the actual impedance on both sides could be different. But once we have a per unit circuit, then if you remember, we discussed that the per unit impedance on both the sides is the same. And if you remember, we also discussed that when we convert the quantities into the per unit, then primary and secondary sides are the windings we can now move. The situation become like that, where the I1 per unit is the same as I2 per unit. So I hope you remember this particular discussion. So let me, I think the marker writing may not be that visible, so let me now make it like that. So if you remember, we have already carried this discussion. So in the per unit case, the transformer windings can no more be considered, and we have the same current when we talk about the per unit per unit quantities, and also the impedance when we talk about the per unit quantities is the same. That's why transformers are, I mean, on the nameplate, or the transformers usually the impedances are shown in I mean one value, either in percentage or in the per unit quantity. So I mean the transformers, they will we will we will only consider the leakage impedance. So transformer will be modeled only with the leakage impedance, and also doesn't matter whether it is the positive sequence impedance or the negative sequence impedance or the zero sequence impedance. The circuitry remain the same. Leakage impedance will not change if the sequence impedance is changed, because these are static elements. So the geometry or the winding arrangement is the same. It doesn't matter whether it's a zero sequence current or positive sequence current or negative sequence current, because we are only considering the leakage impedance. So, however, due to transformer winding connections, because you know that it's a delta Y, whether Y is neutral point is connected to the ground or not, so all these are different cases. Zero sequence current may not have a part to the flow, provided that the neutral is not connected to the ground, or some other cases that we will discuss now. In that case, we will have an open circuit for a zero sequence current. So we will discuss those cases. One case is if, let's say, the neutral point is not connected to the ground. Then obviously we have discussed even before that there will be no path of the zero sequence current to the ground. So we model this transformer only with the leakage impedance, and all the three impedances, sequence impedances, are the same, equal to the leakage impedance. Now some further discussion that sequence impedances transformers, since we have delta Y connections, and that you may know that also they involve phase shift of HV and LV, I mean high voltage and low voltage sides of positive sequence voltage. So also the phase shifts are there. So zero sequence impedance, I mean one can, you know, I believe you know about these phase shifts from the discussion on the transformers. So I will not go into the details of these phase shifts. Zero sequence impedance will depend on the winding connection of two sides of transformer, as I mentioned. That zero sequence impedance, it depends on the winding connection, whether we have a delta on the primary side, or I mean Y connection, Y delta, grounded, I mean all those different cases. So we will now consider the sequence impedances, the zero sequence impedances, because depend, whether we have Y connection and neutral point is connected to the ground or not. So we will consider different situations now to talk about the zero sequence networks. So now let's take the different situations, because you know the primary, I mean a transformer, either the primary side can be Y connected, secondary can be Y connected, can be delta connected, could be the other way around. So these are the different situations. So let's talk about the zero sequence network when we have these different situations. So we will majorly discuss three cases. First, we are talking about the case where we have a transformer, both sides are primary and both sides have Y, the neutral point, connected to the ground. So Y connection with both neutrals grounded. Both neutrals are grounded. There is a path for the zero sequence current. You know that. I mean, if the neutral point is grounded, there will be a path of the zero sequence current to the ground. That we have discussed before. If let's say the neutral point is not grounded, we have discussed that the zero sequence current will be zero. So, but in this case where both the sides are primarily connected and they are connected to the ground, so the zero sequence current will flow, and this is the case is shown here. You see the primary and secondary side. As I mentioned, that in the per unit quantities, I mean the currents on both the sides are the same. So, and we model the transformer only with the leakage impedance. So, and in the moment we are talking about the zero sequence networks, because the other networks, the the zero sequence current flows only through the impedance to the ground. The other two sequence current do not flow through the impedance to the ground. So that's why we are only discussing about the zero sequence networks. And as I mentioned, that the transformers are only with the zero, only with the leakage impedance that are the same as positive, negative, and zero sequence. So they are equal because we have static elements and all are equal to the leakage impedance. So in this particular case, because both sides are connected to the, neutral are connected to the ground, so we have a path for the flow of the zero sequence current. So this is one case where both sides are Y connected and the neutrals are connected to the ground, so we have a path for the zero sequence current through the the grounding impedance. So there is a path for the flow of the current of, zero sequence current in both the primary and secondary side. So this is one case. The other case is that let's say if we have a Y connected, let's say on the primary side connected to the ground, but the other side is not connected to the ground. So we discussed that even before when we were discussing the Y connected loads, also when we discussed the synchronous generators, and we discussed that if the neutral point is not connected to the ground, then there will be no path for the flow of the current through the zero sequence, through the grounding impedance, meaning to say that the zero sequence current will be zero. Because if there is no path to the ground, the zero sequence current is zero. We discussed that before. So let's say now this is the case where the primary side neutral point is grounded, the other side is not grounded. So on the primary side, we have a path to the ground, but there is no path of the current on the secondary side. So as there is no path on the path to the ground on the secondary side, so obviously it's a transformer where induction phenomena is involved. So no path for zero sequence current in secondary. So on the secondary side, as the neutral is not connected to the ground, meaning to say that there is no path for zero sequence current in the secondary side. So it would mean that as it's these are transformer, induction phenomena is involved. So meaning to say that zero sequence current in the secondary side is zero because there is no path to the ground. So the zero sequence current in the secondary will be zero, which means that also the zero sequence current in the primary is also zero because both are Y connected. Both these are Y connected, and the secondary side Y is not connected to the ground, which means that there will be now zero sequence current on the secondary side, and correspondingly the current, the zero sequence current on the primary side will also be zero. So that's why the zero sequence network is open. So this case is different than the one we discussed here. As in this case, both sides were connected to the ground, so we have a path for the zero sequence current on both the primary and secondary side. In this case, because the secondary side is not connected to the ground, which means that there will be no zero sequence current on the secondary side, and correspondingly, because it's a transformer, there will also be no path for the zero sequence current on the primary side, so the circuit is open. Meaning to say that there will be no zero sequence current in this particular case where both the primary and secondary side are Y connected and the secondary side Y is not grounded, so the zero sequence network is open. No zero sequence current. Now let's take another case where we have primary side Y connected, neutral is connected to the ground, and secondary side is delta connected. And if you remember, we made this discussion before that delta can be equivalently represented as a Y connection, and the each phase impedance will be equal to Z delta divided by 3. And if you remember, we also discussed that the current in that equivalent Y will be the line currents which will feed the delta connection, but these are not the current flowing inside the delta connection. We discussed this, I mean, before. So in this particular situation, as Y is connected to the ground and secondary zero sequence current circulates because it does not leave the terminals, it only circulates in the delta connection. So the secondary side zero sequence current circulate in the delta connection, and since there is a ground return path for the Y connected, so the circuit will look like that. As I mentioned that in the delta connection, the currents only circulate in the delta connection, it do not leave the terminals. And on the primary side where the Y is connected to the ground, it means that there will be path to the ground and that will not be connected to the secondary side. So secondary zero sequence current circulates in delta, and since there is a ground return path for the Y connected primary zero sequence can flow. Note that now zero sequence current can leave or enter the delta. As I mentioned, it only circulates inside the delta, but it do not leave or enter into the delta connection. There is an isolation between the primary and the secondary side. So that's what is shown here. Because no current leave or enter the delta connection, it only circulates in the delta connection. So that's why there is an isolation between the primary and the secondary side. So as the Y connection, neutral is grounded, so the zero sequence current flows. But because the secondary side is delta, where neither the current leaves the delta nor enters the delta, so that's why there is an isolation between the primary and the secondary side. The primary side have a zero sequence current to the ground and it is isolated from the secondary side. So now we have discussed these three cases, and with this discussion now I end the discussion on the sequence impedances of the power system components. So now even we have covered the transformers, and now let's take for an example, or for a, let's say, power system where we consider the generation, also the transformers, transmission lines and the loads. Now let's derive sequence networks where we will use the knowledge that we have gained in the previous couple of lectures. So now let's solve an example. So let's say we have an example where we have generation as well as the transformer, and we have a bus where this whole operation. We have a generation that is connected to the bus, and then we have a transformer which step up this voltage for the transmission purpose, and then we have another transformer at the distribution side where it lowers the voltage on the secondary side for use in the for utilization purpose. So this is the whole power system constituting all the different components. We have generation, we have transmission, and we have utilization. So now the generator, as we have discussed before, it is a Y connection, and the neutral point of the generator is connected to the ground through the grounding impedance, that is Zn. A transformer have a delta on the primary side and a Y on the secondary side, and just we have discussed this case, right? The circuit will be isolated for the zero sequence network. We will come back to that point. So this is the transformer where the primary side is delta, the secondary side is the Y connection, the neutral is connected to the ground, but there is no impedance. The impedance is zero. The impedance to the ground is zero. The case is same here. The primary side is Y, the neutral is connected to the ground, without considering any grounding impedance. The secondary side is delta, and then we have neutralization, where we are considering two synchronous motors, where one motor have an impedance to the ground, both are Y connected, and the other motor do not have impedance to the ground. Also, if you remember, we made this discussion that the impedance of the transformer all are equal. I mean, positive, negative, and zero sequence impedances are equal, and we model the transformer only with the leakage impedance. So, but anyhow, the zero sequence network, it depends on the situation, whether we have neutral connected to the ground or not, or some other situation that we discussed. So the transformer X1T, which is this transformer, X1 of this particular transformer, which is the positive sequence inductive reactance, that is equal to the that is equal the X1T, which is transformer 1, is equal to X2 T1. So for transformer number 1, the positive and negative sequence inductive reactances are equal. Similarly, we have the case here. X1 T2, which is transformer number 2, is equal to X2 and transformer number 2. And for the lines, as we have discussed already, that the positive and negative sequence impedances are the same. We have carried this discussion in the last lecture. Anyone, I revised it in the beginning of this lecture, that positive and zero and negative sequence impedances are the same, and we are only considering inductance of the transmission line. So that's why X1 of the line is equal to X2, which means positive sequence inductive reactance is equal to negative sequence inductive reactance. And if you remember, we also discussed that the zero sequence impedance is approximately equal to 3Z1. So X0 will be approximately equal to 3X1. So now, as we have discussed individually the sequence impedances or sequence networks of the generator, transformer, transmission line as well, so and also loads, we also we have discussed the sequence impedances or sequence networks of loads, Y connected loads, transmission lines, rotating machine, and transformers. So we have all these components here in this particular network. We have a generation, we have transformer, we have transmission lines, and we have loads. So all these four components we have separately discussed. So now, using that information or using that knowledge, now we will derive the sequence networks including all these components, and we have discussed some important point here as well. So now let's say the positive sequence network, as we have discussed that, if you remember, we discussed that for the case of the generator, we have voltage source only in the positive sequence network. We have discussed this point before when we were discussing the synchronous generator. So that's why we have, for the positive sequence network, we have a voltage source. That is what we call as EG or E1 or EA, whatever you call it. So this is now E1, or we also called it basically EA or EG, whatever you call it. So this is the voltage generation, the generated voltage. And if you also remember, when we were discussing the synchronous generator, we discussed that theoretically the positive and negative sequence impedances are the same, and zero sequence impedance is equal to, the Z, the phase impedance plus the 3Zn, which is the impedance to the ground. And in practice, we discussed that in practice, Z1 is taken either as the steady state or transient or subtransient inductive reactance, and Z2 is approximately taken as the subtransient inductive reactance, and Z0 is taken as, the leakage reactance. So now using that information, we are not talking about the Z, the positive sequence, so we will consider either of these terms. So here in this particular case, the Z1 is taken as the, or the X1, let's say, if we are only talking about the inductive reactance, so X1 or Z1 is taken equal to the subtransient inductive reactance. As I mentioned, that Z1 can be either of these terms. So this is in the positive sequence network, Z1 represents the positive sequence impedance, so it is taken as subtransient inductive reactance of the generator. Now afterwards we have the transformer, and we have discussed that the positive and negative sequence inductive reactance or the leakage reactance are the same, because we model transformer only with the leakage reactance, and positive and negative sequence leakage reactances are the same, because we have static elements that do not change whether we have a positive sequence current or a negative or a zero. So positive and negative sequence inductive reactances are the same. So now in this particular, for this particular network, this is basically we are considering positive sequence network, so we consider the voltage, the subtransient inductive reactance is taken as Z1, and then we have the X1 of the transformer 1. Then we have transmission line, and we have already discussed that positive and negative sequence impedances are the same, and in this case we are only considering the inductance of transmission line. The resistance is taken as 0. So now we have the X1 of the transformer of the transmission line, and then we have this particular bus where we have another transformer, so this is X1T2. So this is the positive sequence inductive reactance of the transformer 1, and this is the positive sequence inductive reactance of the transformer 2. And then we have on the point on the bus end, we have two Y connected synchronous motors. So once again, as I mentioned, we will take the Z1 as the subtransient inductive reactance. So, and since we are considering the positive sequence network, so now this is the two are in parallel, so these two are in parallel. But if you remember, we have, in one case the Y have no neutral, no grounding impedance, and in the other case we have the grounding impedance. So in the positive sequence, because doesn't matter, because this will only affect the zero sequence network. So we are considering now the positive sequence impedance of the motor equal to X double prime, which is the subtransient inductive reactance of motor number 1, and that of the Z1 of M2, this is M1, this is motor 1, and ZM2, which is motor number 2, that will also be equal to double prime the M2. So that is shown here, and we are because we are considering the positive sequence network, that's why we are considering also the voltages in the positive sequence network, because we have discussed before that in the case of the synchronous machines, although we didn't discuss the synchronous motor, but we discussed the synchronous generator. So the similar applies here, that in the positive sequence network, even if these are synchronous motor, we will consider the voltage source. So these two are the voltage sources for these two Y connected motors, and these are the subtransient inductive reactances, the positive sequence reactances, and the rest we have discussed. So this is now the positive sequence network for this whole arrangement, or for this particular network where we have generation, transmission, and utilization. So this is now the positive sequence networks, where we have only considered the positive sequence impedances, and we also considered the sources, because we are discussing the case of the positive sequence network. Now let me also draw the negative sequence and the zero sequence networks. So as you know, we discussed that in the case of the negative sequence network for the synchronous machine, there is no voltage source. I mean, neither in the negative sequence network, neither in the zero sequence network. So this is important to consider. Also, I mean, another point is that we will still take the negative sequence impedance as the subtransient reactance, because positive sequence impedance can be either of these terms, but the negative sequence impedance is approximately equal to the subtransient inductive reactance. Since we have taken Z1 also as this one, so I mean in the negative sequence network it will also be the same term. So now accounting for these two facts, where in the negative sequence network we do not have voltage source, and also considering I mean the negative sequence reactance is still for the synchronous machines as the subtransient inductive reactance, the network can be drawn like that, because transmission lines have the positive and negative sequence inductive reactances are the same, and also for the case of the transformer. So now accounting for these two facts, we do not have a source here, because now we are talking about negative sequence network, and we know that in the negative sequence network there is no voltage source. Also the voltage sources now here are 0. So putting these three equal to 0, we will get this particular case. So now this is the negative sequence network, the same as this one, but the only difference is that we make now the sources as 0. So this will be the case now. So this is simple. We have discussed already this in detail. So by analogy, putting the sources equal to 0 and still considering the negative sequence reactances of the synchronous machine as equal to the subtransient inductive reactances, we get this particular network. But when we consider the zero sequence network, now I would like to ask you to pay a bit more attention, because if you look to this network, we have a delta Y connection where the Y have a part to the ground, but the delta, here, as I discussed this case, that if we have the transformer where the Y is connected to the ground and delta is also on the secondary side, it doesn't matter whether it is the other way around. We discussed that in this particular case there is an isolation between the primary and the secondary side. Doesn't matter whether delta is primary or delta is secondary, there will be an isolation between the primary and secondary side, because we discussed that in the delta connection, the currents, basically zero sequence currents, it circulates. Neither it enters into the terminals, neither it leaves the terminals. It only circulates. And on the Y and the primary side, which in this case is the Y connection, and the neutral is connected to the ground, so we will have a part to the ground, but there is an isolation between the primary and the secondary side. So now taking this into account, and also taking into account that the zero sequence impedance of the synchronous machine will now also include this term Zn in these two cases, because in the case of the second motor here the impedance to the ground is 0, but in case of the generator and also in the case of the one motor there are impedances to the ground. So we have to take these two now, because we have discussed that the Zn, which is the impedance to the ground, it only appears in the zero sequence network. And if you remember, we also discussed that the factor 3. So now accounting for these two facts and also accounting for the fact that there is no connection between the primary and secondary side, similarly will be the case here, we can now draw or can discuss the zero sequence network. So you can see here the point K is no more connected to the point L, because the primary and the secondary side are isolated. So you see here, and similarly the case here, point M and N are no more connected because there is an isolation between the primary and secondary side. So these 2 points are isolated. And X1, X node of the transformer, which represent the zero sequence the leakage reactance of the transformer. Similarly, X0 of the line, which is approximately taken as 3x1. So here it is written as X0, which is approximately taken as, this is taken as X0 will be equal to 3x1, that of the line, when we talk about the zero sequence network. And the same, this is the same. And once again, there is no connection between point M and N, because the primary and secondary sides, due to the Y delta connection, where Y is grounded, delta connection on the secondary side, they are isolated. And now once again, as I mentioned, that now we are talking about the zero sequence network. So this Zn has to be taken into consideration. Also, we have to multiply it with the factor 3n, because in the zero sequence network, the opposition offered to the current I naught is 3Zn. So that's why, and here there is no Zn. So for the motor 1, we take the zero sequence impedance as X0, M1 and 3Zn, and this is taken as the same because there is no Zn involved in the case of the second motor. And similarly, on the generation side we have Zn, so that's why 3Zn is also considered here in the zero sequence network. So this is important to consider, that we have now considered 3Zn, 3 factor, we have discussed it before. So we are considering now this factor of 3 and also Zn in the zero sequence network, and we also consider the fact that there is an oscillation between the primary and secondary side, which we show here. So now this is the zero sequence network of the power system, where we have generation, transmission and utilization. So this is the positive sequence network, this is the negative sequence network, and this is the zero sequence network. So now with this example, where we have applied the knowledge that we have gained in the last couple of lectures, and we have derived these 3 sequence network of a power system, including all the necessary components: generation, transmission, utilization, transformers, and Y connected loads. So let me now conclude this whole discussion which we have made in the last couple of lectures. I think it took me 3 lectures to discuss the sequence networks of the Y connected loads, transmission lines, rotating machines and transformers. So we discuss all these cases, and the couple of observations that we made are that the impedance to the ground, let me take that case so that I can discuss that. So the impedance to the ground will only appear in the zero sequence network. And it is also important that if the neutral point is not connected to the ground, then the zero sequence network will be open, meaning to say that there will be the zero sequence current will be 0. So these were a couple of observations that we made, and also we made this observation that the 3 sequence networks, when you talk about the Y connected loads, also about the rotating machine. So we found that the 3 sequence network, they are uncoupled. So we also made this observation, and we also made this observation that the positive and negative sequence currents, they do not flow through the impedance Zn. Only the zero sequence current flow through the impedance Zn, and the factor 3 we have discussed it before. So to the zero sequence current, the impedance 3Zn is offered, or in this case 3x1. So now with this discussion, where we discuss the sequence networks of these components of the power system, and then we solved an example where we applied all that knowledge, because in this example we have synchronous generators, we have transformers, we have transmission lines, and we have Y connected loads, and we discussed the sequence networks of all these components, and then we applied that knowledge and we derived the positive, negative and zero sequence networks of the power system. So with this, now I end this discussion on the sequence networks. So thank you very much once again for your attention, and see you inshallah in the next recorded lecture. So thank you very much once again. Assalamu alaikum wa rahmatullahi wa barakatuh.